Hello everyone, this is Dilip. Today let's talk about support vector machines. Just like linear regression or logistic regression or neural networks, this is another method for supervised learning. Let's go to the presentation. So we have seen what is the advantage of neural networks over logistic regression. It brings non-linearity into the decision boundaries. In the same manner, support vector machines also bring non-linearity into these decision boundaries. So since linear regression and logistic regression are linear, we have the advantage of getting non-linearity using the neural network or the support vector machines. Let's move on. So we already know this is the cost function for logistic regression. So I did not put regulation here, but this is how the cost function looks like. Now, if we calculate the cost function, say for the n cases, say y equal to 1, then this term goes away. And if we calculate the cost function for y equal to 0, this is 0 times this one. So this term goes away. So in the end, removing the constants, we will see when y equal to 1, usually this is the term that serves as the cost function. And when y equal to 0, this particular term serves as the cost function, ignoring the constants. So same thing we'll put in the support vector machine cost function. So a support vector machine cost function looks like this with the regularization. And one more thing you will observe here is the whatever the lambda parameter, regulation parameter is there. Usually here lambda regulation parameter will be there. So this we have removed and replaced it with C over here. So this is the notation for support vector machines. We will not go into the calculations or much deeper into it because it's a lot more complex than it looks like for the mathematics and all. So just assume this C as 1 by lambda. Okay, just assume this C as 1 by lambda. So 1 by lambda when you multiply, anywhere this regulation lambda goes away. So that's how we look at C. So this is the logistic regression hypothesis. So whatever the features we have, we multiply them with the weights to get the hypothesis. And if you want a, so this is for the linear hypothesis, and if you want a non-linear hypothesis, we can go with this manner. But this is computationally intensive compared to neural networks or support vector machines. So here we are going with a higher degree polynomial, that's why we get a non-linear decision boundaries. The swim hypothesis looks like this: theta 0 f0, theta 1 f1, and theta 2 f2. So as you can see, this hypothesis, whatever the features we are taking, these are not the input features. So these are the calculated features. Similar to neural networks, here also we have calculated features. So how we calculate these features? Let's look at them. So there is something called similarity function. So these features correspond to the calculation after doing the similarity function calculations. So how do we do it? So let's say we have only two features, x1 and x2. So these are the input features, and I will tell you how to take these landmarks. So these are called landmarks. So we select some points in a higher dimensional space. Let's suppose we have here, since we have two features, let's say we have the third dimension where you put some landmarks. and landmarks are nothing but just another set of data points. Okay, you just put them in a different dimension than the whatever the features that you have. So these are in third dimension, and you measure the distance between the existing features and this landmark. Okay, so and you do some calculation, and then you get the similarity function value for this landmark from x1 and x2. Similar manner, you do the similarity function calculation for this landmark. Okay, so I'll explain again how we calculate that. So what we are measuring is the vector distance between this point and x1, between this point and x2. So we are calculating the vector distance. So this is one example. Say for a single point, how we calculate that vector distance and finally put it into this similarity function. So we just take an exponential of vector distance squared x minus L1. So this term, don't be scared of this kind of this function. This is just measuring the vector distance. Say for example, you have x1, x2 features, okay, and the distance from L1 will be x1 minus L1 square plus x2 minus L2 square. That's it. So there's nothing complicated about this upper term, and divided by 2 multiplied by sigma square. So the sigma also, it's a constant which we give. Depending on this sigma, there will be a variation in the support vector machine calculation. So just like regulation parameter we have, this is also another parameter which we need to input that will impact the learning of the support vector machine, whether it will learn fast or whether it will learn slow. So this will impact the learning. You can take it as like a learning rate. So this is how we calculate F1. And this particular calculation, right? This is called kernel calculation. So why we are going with this specific notation? So the reason is this introduces a nonlinearity, and this is a form of kernel calculation. So this is not don't confuse this kernel with whatever the kernel we have in the operating system. So this is just a terminology that started in 1960s and it just stuck with it. So this particular term kernel is called Gaussian kernel or RBF kernel. So mostly in the industry, you will see the term RBF. So RBF kernel means this is the one. This is how the support vector matrix similarity functions are calculated. So if you just replace this calculation with just the subtraction of x minus L1, okay, so then it will be a normal. So we call it a linear kernel. And one more thing is, I have shown you how to get the distance from these landmarks to these features, but how to calculate the similarity functions. But how do you select these landmarks? So a simple way to select the landmarks is number of input features you have. Whatever the input features you have, you just put the landmarks, each landmark corresponding to the input feature. Say if you have 10 features, so you just put 10 landmarks, and each landmark you put the value, its value is equivalent to the input feature. So that's how we select the landmarks, and then we do the calculation for the similarity function. and we use the similarity function output as input features, and we calculate the weights for them, and in the end we'll get a hypothesis that will fit our model. And so this is how the cost function is transforming. So at the outset, this doesn't look many different. This looks same. But if you see the cost function we are calculating, what we are optimizing is not the weights multiplied by input features, but weights multiplied by the calculated features using that similarity functions. Okay. So support determinations are also called large margin classifiers. So why they are called that way? Say if we are classifying between apples and bananas, and if we use logistic regression, so we may get a classifier that looks like this. We may get a classifier that looks like this. So these are like legit classifiers. They are able to classify well. But if you measure the distance between this this decision boundary and the banana, and this decision boundary and the apple, so it's different. So one side it is larger, one side it is smaller. And similar way for this apple is near to it, while this banana is very far from it. So what the support vector machine does is it will result in a classifier that results in a decision boundary that tries to maximize the distance from the decision boundary to the any of the input features. So with support vector machine, we get a classifier like this that separates out the data. So this will be equidistance from either bananas or apples. Okay. So support vector. So this results in a vector that is equidistance from both like both, or say if you are going for the multi-class classification, so which is equidistance from all the classes. So that is what support vector machine is. And sometimes you will hear the term support vector classifier. It's the same thing, support vector machine, support vector classifier. So in the next video, we will take a look in the code, like how to code for support vector machines, and also we'll compare it with neural networks, and in what cases you have to go with neural networks and what cases you have to go with support vector machines. So thanks everyone for watching the video. Bye.